we have equivalent directions, meaning and equivalent planes. So for instance, if you, this is the simplest way of looking at it is to look at this one. Oh, I'm in the edit mode here. So I need to run this. Okay. All right. You can still see the screen? Good. Okay. Thank you. Thank you, Will. So if you look at this, this is a simple one to see. It's a cubic structure. So if you look at the arrangement of the atoms, I'm talking about the plane, 100 plane, it is no different than the plane right if I were to draw a plane here. See? This is no different than the 100, right? And that too is no different in terms of how the atoms are arranged. This plane. Meaning, and if you were to sort of find out what these planes are, you would be able to write for this simple cube, you would be able to write that 100 plane looks the same as 010 plane and looks the same as 001 plane because there's no difference, right? There's no difference in terms of the arrangement of the atoms. So the reason why we are doing this is because of the crystal symmetry. It doesn't matter if we talk about 001 plane or 010 plane, 100 plane, because the electrical properties will turn out to be very similar. The same, in fact, because of the symmetry. So if we are going to connect this to electrical properties, then we would say, well, there is a family of planes that exhibit the same behavior. Okay, so there's a family of planes that so how do we notate family? So this family would be, we would use curvilinear bracket. So if you were to say 100 and put it in this, then what we are saying is that we are referring to family of 100 planes. So look at the symmetry of the crystal that you're talking about, and in this case, it is simple cube, SCC, simple cubic structure. And if we say we are talking about 100 family, then effectively we are referring to all those planes that have a similar behavior, similar look. So which is these three here. Okay. So now you could do the same thing with the directions. So say for instance, this is 100 direction. If I were to say what is 010 direction, so I would say this is 010 direction. What is 001 direction? Then that will be this direction. Let me erase this stuff so that it gets out of the way. So these are the three directions. And if you look at the nature, you begin to see an atom exactly the same distance as you, the environment is exactly the same as you would have for 100, 001, or so the family of directions is given by this. If I were to say this bracket, I use this bracket, then I'm referring to family of directions. Okay? I don't think this is in the book, but this is good to know that families of directions are given by this bracket, family of planes are given by this bracket. And the idea of family itself is important because of the crystal symmetry, right? So, all right, okay. Any questions at this point?
Sorry, could you repeat that? The square brackets are representing the planes, the family of planes?
No, the square brackets represent direction.
Direction.
Like
Okay.
100 is a direction, right? But if I use this bracket, then it represents family of 100 direction. And in family of 1, 0, 0 direction, one would include 0, 1, 0, 0, 0, 1 as well in this particular example because of the symmetry. So this represents family of directions, and then same applies for planes. So if I use this bracket, then I'm referring to family of planes. Does that answer the question?
Yes, it does. Thank you.
Okay. All right. So let me clean up my slides. Now, this is what I mean. You can write notes on your slides or on the side or add them later if the slide is posted later. Because I don't save this. I don't save my own scratch work here. Okay, so we went through this. Okay, this is, okay. I think this is where we were. Correct me if I'm wrong. Did we start talking about this diamond structure? I think we just began. Is that true?
Yeah, you just started on this slide and then we had to end.
Okay, good. So this is where. So let me spend some time because this is actually silicon. So remember what is diamond? Diamond, of course, is made out of carbon atoms, and carbon comes from the same periodic table as, the same column as silicon and germanium. So, properties you would expect to be similar. Now, if all these atoms were carbon, then this would be a diamond crystal, diamond primitive unit cell, you might call it, if it was real diamond. But this is silicon. So since it behaves, the structure is the same, we simply call it a diamond structure for the sake of any better name. Suppose diamond, everybody recognizes diamonds. All right, now, last time we said that the way that I like to look at it is that this is an FCC lattice. Now, if you recall, what is an FCC lattice? FCC lattice is face-centered cubic. Okay? Face-centered cubic is a cube and plus 4 atoms. Let me just complete the sentence. Plus 4 more atoms that are inside. So what is face-centered cubic? Face-centered cubic is all the 8 corners, as you can see, 6 faces, so this is a face, this is a face, this is a face, center of the faces, this is a face at the bottom, this is a face, and then in the back, there is a face. So there are 6 faces. So that's where the atoms are located. Plus, in addition, what you have is 4 additional atoms. Now, the 4 additional atoms are inside the cube. They are not on the surface of the cube or the corners. They are inside the cube. So which are those 4 atoms? Well, one of them is highlighted. Okay, this one is highlighted. So notice that this atom connects to a corner atom this way. It connects to a face atom this way. It connects to another face atom this way. And it connects to another face atom right here. So each silicon atom, all of them are silicon atoms. Each silicon atom connects to 4 nearest neighbors. So that's a key. Okay. So 4 nearest neighbors are, let's see, where's my, okay. There are 4 nearest neighbors, and those are the 4 nearest neighbors. And this pattern you can pretty much repeat for every atom. Now, in the picture, of course, for clarity, we just show this as a corner atom. But effectively, if you just build this crystal out left, right, center, up and down in 3 dimension, then this atom would also have exactly the same 4 nearest neighbors, the way that this one has. Essentially saying that you could move the origin around anywhere. You don't have to start the origin here and create your cell, but you can move the origin anywhere and you would find exactly the same pattern being repeated. This 4 nearest neighbors, if you were to give it a name in geometry, you would call it a tetrahedral in 3 dimensions. So this is the atom, and then it connects to 4 nearest neighbors like this. And in 3 dimension, it would form a tetrahedral. Now, let's take a look at where are they located. Now, the picture here is not very good, but the way that to visualize it is the following. I'm going to try to draw it here. Let me erase this actually first. Now, maybe we can try in this picture itself. Okay, let me try in this picture. Let's see. Okay, maybe this is the side that would be better. Take this corner, follow my pen. Take this corner and take this opposite corner. So if you're in a room and imagine that room to be a cube, take the opposite corners and join a line between these opposite corners. Just imagine in a room as well. Oh, my hand is not steady. So let's say this is the diagonal. This is the body diagonal from this corner to this corner, okay? So this body diagonal, the inside atom, the 4 additional atoms that we're talking about, appears 1/4 the distance along the body diagonal, okay? So 1/4 the distance of body diagonal. I don't know why it keeps drawing that line. Okay, so this atom appears 1/4 along the body diagonal. And notice it's in the bottom half of the cube. So the cube center is somewhere here. So this is in the bottom half. If you go exactly to that opposite corner, which is this, you'd find another atom there. Okay, so effectively, you draw a body diagonal from here to there. Okay, I didn't get it straight, but 1/4 along this body diagonal. So this is the body diagonal. 1/4 the body diagonal from this atom, you have that atom, additional atom. Okay, does that make sense?
Yeah, I'm following you so far.
Okay, good. Now, you do exactly the same thing for the top layer. Use this body diagonal and come down from the ceiling a 1/4 distance along the body diagonal and place an atom there. Okay, and do the same thing from this corner to this corner, bottom here. Oops, let me get rid of some of these. Otherwise. Okay, so you do the same thing from this corner to this corner. So imagine your room, you're choosing opposite corners, and then go 1/4 distance along this and place an atom here. So these 2 atoms are in the upper half of the room along the body diagonal, and this atom and this atom are at the bottom half of the room, but in the opposite corners. So that's where they are located, okay, the inside atoms. All right. Any questions on this? No? Okay, good. So 1/4 along the body diagonal, this is the best way to sort of visualize it and use the room. You imagine your room to be a cube and follow that. Now, of course, all the atoms are silicon atoms, right? All the atoms are silicon atoms, and or germanium or carbon. So, of course, we are interested in semiconductors, so we are talking about silicon and germanium in this case. Now, the picture in the next slide, if there are no questions on this, you can visualize diamond structure, then we'll go to the next one, is for a compound, okay? So the question then is, gallium arsenide is also a semiconductor, but it's a compound. So what is its crystal structure? Now, it turns out The gallium arsenide also, the atom placements are in the same pattern as silicon. You notice that it's a FCC lattice, face-centered cubic lattice, and there are 4 additional atoms inside, and locations are the same as it would have been for silicon. So if this is gallium, this is gallium, this is also gallium, and this is gallium. And the rest are arsenic. So this is all arsenic, the white ones. Okay? So all of these are arsenic. So gallium, 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 these are the interior inside atom, and the face-centered atoms are all arsenic. So I would say face-centered atoms are arsenic, and 4 additional atoms inside are gallium. Now you would say, why don't we call it a diamond structure? Well, it's not really a diamond per se, but it exhibits the same locations. It's just given a different name. It's called a zinc blende structure, because it's a compound and there are 2 different elements. So it's called a zinc blende structure. Now here's a question, and I'm hoping somebody would sort of respond to it, try to make it interactive. Gallium arsenide is, when you look at chemistry, you would say for 1 gallium, there is 1 arsenic, right? Stoichiometry would say so. True?
True.
If you think, right? I mean, if you think of your chemistry, when you say, I have a compound and it is, pick a compound, CH4, okay? So for 1 carbon, you have 4 hydrogen, right? So that's a stoichiometry, right? So here we are saying gallium arsenide for 1 gallium and there is 1 arsenic. But in this particular picture, I show 4 gallium atoms and a bunch of these corners are arsenic. How do I sort of justify? And this is the primitive unit cell, meaning if I repeat this in 3 dimension, I'll get the whole crystal. So is this stoichiometric? Is there a discrepancy in this? Or how do you explain it if there isn't? Is the question clear?
There are electrons, or
Say that again.
they share electrons when they bond.
But we are talking about the number of atoms, though. I mean, if you started counting the number of atoms, you would say, how many arsenic atoms are there? 8 corners and 6 faces. So that's 14 arsenic. I'm putting a question mark. 14 arsenic and 4 gallium. Let me erase this. 14 arsenic and 4 gallium. Then the stoichiometrically, should we write this? I'm putting question marks. I'm trying to help you think.
I think just the galliums that go with the arsenic, like on the corners and the faces, aren't shown, but they still exist in the crystal structure.
Gallium goes with arsenic.
So we're showing the gallium, and we're showing all the arsenics that are bonded to galliums. We are not showing all of the galliums that are bonded to individual arsenics, right? So we have a lot of chopped bonds on those arsenic pieces that would extend out and connect to a gallium. So the ratio still appears to be 1-to-1.
True, that is true. We don't see those. So, well, you say it appears to be 1-to-1, but there is plenty of information here to decide whether it is 1-on-1. What you said is correct. But how could you, first of all, is this correct?
I don't think that's correct. Isn't it because we established that for FCC, it's like 4 atoms because the corners are only 1/8 and the face are only half. So the total would be 4, which means they're actually equal.
Exactly. So that's the answer. Turn on your video if you can, please, and tell me your name so I remember a few names.
I'm not
Okay,
well
yeah.
dressed, so if
again?
I don't turn on my video.
Okay, don't turn on the video. Tell me your name.
Oh, Stephanie.
Stephanie. Okay, thanks, Stephanie. I don't want to say thanks caller or thanks student who responded. So now at least I can say thanks, Stephanie. All right, so that's the answer. So the answer is it's not 14 arsenic. Remember, this arsenic is being shared by 8 total cubes. So the contribution of this arsenic to this primitive cell is only 1/8. Remember last time that we said that. So there are 8 arsenic and only 1/8 is in part of that cube. And there are 6 on the faces, only half of it is part of that cube. So this gives me what? 4? So in this primitive unit cell, I have 4 arsenic. Literally, I have 4 arsenic contributing to this and 4 gallium. So the stoichiometry indeed then is not this. It is gallium arsenide. Okay, so it's just a sort of keeping in mind that when we look at these atoms, we know that they are being shared, which effectively is what you said, is that, there are other things going on around it. So what is the contribution? So essentially, you have to look at what is the contribution of this to this particular cell, right? It's contributing to other cells as well. Now, example here is gallium arsenide lattice. It says, I'm going to add indium phosphide as well. So there are several compounds that show zinc blende structure. So in terms of location, it's again 1/4 along the body diagonal. Okay, but they are shown in different colors, of course, because they're different atoms, and also because the size of the atom could be different, right? So gallium is shown as a bigger atom compared to arsenic. Okay, so now that we know that, let's get rid of some of this. Okay, any questions on this? No? All right. So now, what about bonding? So what about, now this is a separate section called atomic bonding. From chemistry, we know what is ionic bonding, right? Example is sodium chloride, where it's actually transfer of an electron from one side to the other. So group 1 and 7, sodium comes from group 1 and chlorine comes. So if you remember, it becomes Na plus and Cl minus. Okay, so Na plus and Cl minus. So this is called ionic bonding. So they are held together because there's electronic charges that hold it together. So that's ionic bonding. I'm not going to repeat this. The book goes through, and you must have seen this in basic chemistry. Covalent bonding is, of course, when electrons are shared between 2 atoms, right? So, and this happens in group 4. So silicon or germanium is of interest. So this is covalent bonding. Now, when we say group 4, essentially what we mean is there are 4 valence electrons, right? 4 valence electrons. And since it has 4 nearest neighbors, right? So each, the next slide will show that. So let me not sort of draw it here again, that each silicon shares its electron with its neighbors. And that's how the shell is complete with 8 electrons. Of course, there is metallic bonding and van der Waals. I'll let you read this. This is not relevant. But what is important is this. how sharing is done. So we'll come to that next. Okay, now covalent bonding, hydrogen is the simplest of cases, right? So there's one electron, and so the bonding is each hydrogen atom shares with its neighbor, and so that becomes H2, right? So there are you have that covalent bonding that goes on. In silicon, each of these lines, think of it, represents a valence electron. Now, first of all, what is a valence electron? These are the outermost electrons. These are the electrons that are going to participate in bonding. There are more electrons in the inner shell, and they are of less interest right now. But from bonding purposes, these are the outermost electrons, so they are valence electrons. So if you look at the silicon atom by itself, it looks like this. But when it is bonded, so you would see that this silicon atom shares one electron with this, and so does the other one, right? So you see all these sharing one electron with 4 nearest neighbors. And then when you look at this silicon, you find that the shell is complete with 8 electrons, right? So that's 8 electrons. So these bars, think of it as bond. So if it is a bond, it's a complete bonding with the 4 nearest neighbors. Now, this is in 2 dimension, right? So in 3 dimension, of course, it looks like a tetrahedral structure, right? So the crystal structure that we talked about. Okay, this is simple. So covalent bonding. I suppose no questions here, right? Okay, let's move on. Now, if you recall, I had mentioned that starred sections that have a star on them will not be included. Now, here's a qualifier. There are some starred sections that would be included. Most of them would not, but some would be included. And the ones that would be included, I'm going to mention it, okay? So section 1.6, even though it has a star, it is included. Okay. Now, why am I including this? Because this section talks about defects. Now, in real crystal, right? Ideally, of course, every atom should be in the right place and should be perfect. But real life is different. Lattice is not perfect. And it contains imperfections, which are defects. We'll talk about what they are, and impurities. Impurities could be foreign atoms. As pure as you would like to make silicon to be, it may not be 100% pure, though the purity is very high. The purest man-made material ever is silicon. Now, why am I including this? Because these defects and impurities play a very, very important role in silicon. So, I mean, the electrical properties are dramatically influenced by this. So it is important to understand, at least have a knowledge of what kinds of defects and impurities that might get incorporated in a crystal. So what are the different types of imperfections? One general class of, there could be various kinds of point defects, but its class of defect is called point defect. Now, what is a point defect? Point defect is at that particular location, something is not right. So let's say in this particular case, the crystal looks perfectly good, and this is showing just in 2 dimension, but there is one atom that is missing. So this is a missing atom. Clearly, in real life, it can happen, right? So a missing atom is called a vacancy. Okay, vacancies are not only important in electrical properties, but in terms of processing as well. So this is called a vacancy. So need to know this, there are vacancies. And what does that mean? Now, this is a missing atom. What if you have an atom where it's not supposed to be there? We have all the other atoms at the correct lattice points to make the crystal. But there is one particular atom which is somehow got incorporated at this particular point, and it's not supposed to be there. So you can see how the lattice is stretched, effectively saying, if you think of it from a bonding point of view, that the bonds are not, bond lengths and the strength of the bonds in this area are not quite the same as you would have in a perfect crystal. So this, something like this is called an interstitial. Interstitial implies that that it's outside of these lattice points. Okay, so this could be a silicon itself, right? So if all of these atoms are silicon, you could have a silicon interstitial. Okay, or you can have a foreign impurity that can be an interstitial. Perhaps while you were making it, a carbon got incorporated. Okay, or some heavy metals got incorporated. So this atom could be any atom, but as long as the location-wise, it is not part of the lattice, it's called an interstitial. It doesn't have to be silicon, it can be something else. But interstitial atom essentially means is it's within the lattice somewhere where it should not be. Now, in contrast, what I also want to say is that let's say this particular atom, right, silicon atom, is in terms of location-wise, if it was replaced with some other atom, perhaps carbon, not as an interstitial, but it replaced where the lattice atom should have been, then this is called substitutional. So it's not interstitial, it is substitutional. The distinction between interstitial and substitutional is interstitial appears somewhere where there is no lattice point and it's thrown in there. Substitutional implies that it is at the location of the lattice point, but it is, and it is at the location of the lattice point. I think that's sufficient to say. Okay, is it clear? And we will see how intentionally we add impurities at substitutional sites to change, modify the crystal properties, electrical properties. That's why it is important to know these terminologies. Okay. I see. So here is an example of that substitutional. It replaces, it's exactly at the point of where the lattice is. So these are point defects. There is something called a Frenkel defect. Now this is, you have a vacancy and an interstitial defect are near each other, and there is some interaction between them. So this is just, something to remember or know, that combination of point defects have a different kind of terminology and would have different influence. Apart from point defects, there are things called line defects. Now, line defect, as the picture shows, you would have a lattice and it's perfectly fine, up to this point. But then all of a sudden, the whole line of atoms are missing. And as a result, the bonds get stretched and sort of, there's dislocation here. So this is called a line dislocation. And what is this effect? Disruption of a normal geometric periodicity. And it, again, all of these have effect on electrical properties. Okay. I didn't set the alarm, but I'm keeping track, hopefully. I should have. So, Will, since your video is on, just raise your finger or hand when I reach 420. Okay, so we'll stop. Okay, thank you. Or anybody else who has their video on, so I'll notice that. Now, this section, growth of semiconductor material, it is starred. Okay, and this is not included. This is, but it is interesting for you to read through. We already talked about how single crystals are made. And then I'm just going to give you a brief orientation to it. So if you're reading that on your own, just for the fun of it to know, you'll have a sense of what it is. So effectively, this is a melt. This is a silicon melt. It's purified silicon. It's in a crucible. It's heated to very high temperatures, as you can see. And then a seed crystal is lowered into the melt, and then it's pulled. So of course, the temperature of this is very close to its melting point. So as soon as it comes up, it cools and it solidifies. And what you get is you grow this crystal. So the material that is being formed, and slowly you're pulling it, becomes a boule. And I showed you pictures of that boule. This method is called Cherkolsky method. That's just the name. So as you read through, you'll see that how crystals are made. Now, here's an interesting stuff. You'll find that the crystal that is made is essentially the substrate, which provides mechanical support. It's typically perhaps 400 to 500 micrometer thick. This is what a Cherkolsky method would give. By virtue of the nature of how it is made, it is not perfect. It has issues, but it nevertheless is a good crystal. The devices are made on top of it, meaning, or rather, let me put it this way. If this is made out of Cherkolsky method, then we have to deposit another layer of single crystalline silicon on top of it. So the crystalline structure of atoms here acts as a template. And when you deposit silicon on it, this is very high purity and high fidelity, because you use a different process and you make sure that this crystal is perfect or near perfect. And the bottom crystal provides you as a template to grow. This is called an epitaxial layer or epitaxial growth technique. Epitaxy, essentially, the terminology comes from the fact that it is trying to duplicate whatever is underneath in terms of its crystalline structure. The device is made starting from here. Device usually, most electronic devices don't use a substrate. Their substrates are, though that's not strictly true, but I'm just saying it so that you understand that epitaxial layers are very important. There are various methods. These are called chemical vapor deposition, liquid phase epitaxy, molecular beam epitaxy, and MOCVD or MOVP. Not interested in this, but you have the jargon if you are interested. This is for epitaxy. It's called homoepitaxy if you're growing silicon on silicon, right? But if you're growing another different material, such as aluminum gallium arsenide, which is a ternary, remember, onto a binary, which is a gallium arsenide. So these are two different semiconductors. Then this is called heteroepitaxy. Okay. And of course, this grows using the template below. So it turns out that some composition of aluminum gallium arsenide has exactly the same crystal structure and atom orientation as gallium arsenide. So the templates work out perfectly. So you grow them on top of each other and you don't get defects at the interface. Any questions? Worth reading, but this is start. So I'm not going to ask you about these things. We talk about these things in later classes if you do take them. Okay. Summary, we are finishing chapter 1. Silicon is the most common. We already said that. Electrical properties depend upon single lattice structure. There are some definitions here. Silicon is a diamond structure. Atoms are formed in phosphide, Miller indices. So anyways, that summary is imperfections do exist. And this is important, right? So most semiconductor devices are fabricated in epitaxial layer. Cherkolsky gives you the starting point of the mechanical. All right. Any questions up to this point? No? Okay. Let me give you an orientation to the next chapter so that we sort of, I have to stop sharing.
Someone in the comments just asked if we had a homework due soon.
Yeah, we haven't found a grader. So I don't know if we will get a grader. Every semester we normally have a grader. There's one budgeted for it, but I don't know how that'll work out. So I'm giving some thought to it. Give me another day or two. I'm going to check what the prospects are in terms of, and I'll post a homework assignment. And in fact, I might as well, I'm more inclined to that you turn in the homework, whether there is a grader or not. So you do the homework and turn it in, and you turn it in. And I'll post the solution so you'll know the correct answers. I certainly would not be able to go through grading all the homeworks, but at least I'll know that you have done it. So I'll look at your work, and pretty much if you have done it, you'll get the points. I'm more inclined to doing that. But if there is a grader, then of course I'll pass it on to grader, who can go through comb through all the steps and partial credits and whatnot. Okay, so let me do that. I think the more I think about it, the more I'm inclined to assigning homework and that you turn it in. Each one of you, I think, have a drive folder, right? Okay, so you post it in the drive folder. Okay, as long as you have done it, more or less, I'll just scan through. We'll give you the points. If you have not done it, of course, then I'll deduct some points. Solutions.
Correct me if I'm wrong, but doesn't the syllabus say that homework doesn't really have a specific percentage for our grade?
Yeah, but that was, remember also I put a double star on it, subject to change. We were waiting. Okay. We were hoping to see what was going to happen with the grader. But instead of, usually within the first week or so, we do get a grader in a normal semester, but this semester is unusual. So let me just go through, assign some grades to homework to bring up your thing. And you would turn it in, but I may not be able to go through as in a detailed way as a grader might. Okay, but that forces you to turn it in. Does it answer the question?
Yeah, thank you.
Okay, so I'll post the homework either today or tomorrow. And typically, so today is Monday, I'll post it today. And usually you would have a week to do the homework. So since we are done with chapter 1, I'll post the homework on chapter 1. Any other questions before we move to, how are we doing on time?
We're just about out. We've got about a minute.
Yeah. Okay. So I won't start this PowerPoint. But chapter 2, do read ahead. And quantum mechanics might sound a little scary or, but what we are going to do is we are going to approach it in a way that it'll give us an insight into, what will happen later in the chapter. So I'm not going to get into the details of it, but just enough, just sufficient so that we understand from chapter 4 onwards what semiconductors are about. So if you are reading ahead, skim through to see what the topics are and just get a general handle on it. I will go through in a different sort of I shouldn't say different. I'm going to follow the book, but might skip several issues that are in the book because they would not be necessary to drive home the point that I need to. So I'm going to follow the lecture. in terms of study. So whatever we do in the lecture, follow that. But if you read ahead, you'll have a sense of what it is.
Professor, we're at time.
All right. Thank you, Will. Okay. Hopefully you filled out your attendance before you go.